Hello, the objective of this lecture is to provide an introduction to the different types of loads that act on civil and architectural engineering structures. We won't address the calculations of those loads in this lecture. We'll just provide a general description and classification here, and then dive into the detail of the calculation of those loads in other course modules. Let's get started. As a starting point, both the International Building Code and ASCE 7 define loads as forces or other actions that result from the weight of all building materials, occupants and their possessions, environmental effects, differential movements, and restrained dimensional changes. There are a lot of ways to classify loads, however, and some of the most prevalent ways of classifying them are based on their direction, whether it's a lateral load or a gravity load, whether it acts upwards or downwards. Another is the nature of the load, permanent versus variable or transient, environmental or meteorological, or an earthquake load. The structural response that they impose also is another way of classifying them. Static versus moving, dynamic load versus vibrational, impact versus blast, etc. And then the action that it creates on the building. It could be an external load or it could be an inertial force. It could be a ground movement or a settlement, thermal expansion, contraction. It could be pre-stressing or post-tensioning. And then lastly, there are also notional loads that we'll define later. This figure comes out of the Tally textbook and gives an idea of how all of the different loads are grouped. So you have the different actions that are acting on the structure. So you have loads that you have dead load, live load, impact, etc. Then you have environmental loads, wind, snow, earthquake, and then constraint loads, which would be primarily temperature, creep, shrinkage. I would tend to treat earthquakes a little bit differently than wind or snow, but that's splitting hairs to some extent. I think that when the Tally textbook was released in 2003, it might have been considered one way, and there's been a bit of a shift in the way earthquakes are handled. Now for some notation that's used in the ASCE 7 standard. The primary loads that we consider are these that are given here: dead load, the live load that's on the roof, rain load, snow load, wind, and earthquake. There are a lot of other loads as well, and they're not any less important. It's just that when we work through examples and problems in this class, we probably won't consider them to the same extent that we do the others. So we have weight of ice, the wind acting on ice, earth, bulk materials, excuse me, fluid loads, flood loads, etc. Now the self-straining load, T, includes a lot of different aspects. It includes temperature changes, shrinkage, moisture changes, creep, movement caused by differential settlement, and then combinations of all of those different things. Now, if you're going to work in bridge design, the notation that's used there is a bit different and it's a bit more extensive. They categorize the loads right from the beginning as permanent or transient. So here are the permanent loads. So the DC loading is the weight of the structural components and the attachments. DW is the weight of wearing surfaces and utilities. And they treat that differently because the wearing surface could be changed over the life of the structure. Utilities could be added to the structure over the life. Then you have different locked-in effects for earth and horizontal pressures. Transient loads, there are several of them. You have the live load, the weight of the vehicle. You have the dynamic load allowance. The vehicles passing over bridges are moving inherently, so they create dynamic effects. And then you have a lot of other different effects there as well. The effect of a vehicle braking on the bridge, a vehicle turning, vehicles colliding with the bridge, a vessel colliding with the bridge. That's a ship or something passing underneath the bridge. It's colliding with it. Other loads that are used in the AASHTO specification include water load, wind on the live load, wind on the structure, earthquake and ice, and then finally the self-straining loads due to temperature, shrink, creep, and things like that. We're not going to focus on bridges a lot in this class, but I will touch on them where it's appropriate. Okay. Dead loads include basically all of the self-weight of the structure. So That's not just the weight of the structure itself, but also the weight of the non-structural elements, including ceilings, built-in partitions, finishes, cladding, etc. Now, the partition load is a little bit different. There are built-in partitions like masonry walls and things like that, but there are also movable partitions like gypsum board on metal studs or gypsum board on wood studs, things of that nature. If it's a movable partition, it's part of the live load. If it's a built-in partition, it's part of the dead load. Okay, these are all considered to be gravity loads, and they're considered to be permanent. Okay, live loads are produced by the occupants of the building and do not include any construction or environmental loads that are due to snow, rain, etc. So basically, if it can move within the building, then it's a live load. So obviously, people that move in and out of buildings are going to be considered part of the live load. But also desks and filing cabinets and things like that are also considered to be live load. Even though they don't move very often, they can move, and thus they are considered to be part of the live load. Okay, roof live loads are handled a little bit differently in our designs. Roof live loads tend to be caused by maintenance workers or things like that. Maybe people checking on air handlers or HVAC units are on the roof, or maybe people washing windows and things of that nature. So roof live loads tend to be much smaller than live loads on the main floors or the main levels of buildings. Okay, like dead loads, live loads are also considered to be gravity loads, but they're not permanent, of course. They're transient or variable loads. Okay, rain and snow are loads that are due to the accumulation of rainwater on a roof, or the accumulation of snow on a roof, or the accumulation of both snow and rain. So if a roof is properly designed, there shouldn't be any rainwater accumulating on it at all. Maybe in the rare case of a very large storm or something like that, but the roof should be designed to drain properly. Excuse me, we can accommodate snow, and sometimes you have to worry about having a snow event and then rain following it, so the snow gets wet and heavy. Okay, both of these loads are considered to be gravity loads and environmental loads. Okay, wind loads are basically the aerodynamic action of wind acting on the structure. Wind creates both lateral loads with a positive pressure on the windward face and negative pressure on the other three faces of the building. And it creates vertical loads as well. It creates negative pressures on flat roofs. So when a wind passes over a building with a flat roof, it creates uplift. It creates either positive or negative pressure on the windward faces of sloped roofs, like a gable roof on a house, and it creates a negative pressure or an uplift on the windward face of a sloped roof. Okay, wind creates both external and internal pressures, right? It blows against the outside of the building. It creates a suction against the outside of the building, but it also creates an internal pressure within the building, and that has to be accommodated too in most designs. Finally, wind is considered to be a lateral load, and it is an environmental load. So consider wind acting on this structure. Wind is blowing from left to right in this case, and on the windward side, it creates a positive pressure or a force against the face of the structure, and on the leeward side, it creates a suction or a negative pressure. When it passes over a flat roof, it creates a suction upwards, a negative pressure, which results in an uplift on the building. Okay, if we look at the building in plan, then you can see the positive pressure on the windward face again. You can see the negative pressure on the leeward face again. But in this view, you can also see the negative pressure acting on both the side walls. So this image shows wind passing over a building with a gabled roof, like a house or a small building. And you can see that on the windward face here, we have a positive pressure. On the leeward face over here, you have a negative pressure or a suction. And because this roof is sloped created with a high enough slope, you can see a positive pressure on the windward face of the slope roof and a negative pressure on the leeward face. depending on the angle of that slope, as the angle goes from 0, a flat roof, up to something like a 45-degree angle, then the forces on the windward slope portion go from a negative value to a positive value. And you can see that in this image here, where this is drawn in 3 dimensions. And you can see that on the windward part of the sloped roof, that force could either be positive or negative. It could cause a pressure or a suction at that point. When you look at the action of lateral loads on buildings, this is showing wind load, but it's also true for other lateral loads. There are a couple of different actions that are created. So the wind blowing against the side of the building could create the tendency for the building to slide, or it could create the tendency for the building to overturn. And we have to guard against both of those different actions. So we have to make sure that we anchor the building into the ground such that it can resist both sliding, and we have to make sure that we anchor it down so that it doesn't topple over. Now, gravity loads in a lot of buildings are large enough that it resists the overturning action, but sometimes that's not the case. Okay, this is a similar idea for a larger structure, and this is a multiple story building with a basement, so this would be an office type building. And in this case, you have to worry about the different actions due to gravity loads shown in this image, or due to lateral loads in this image. So look at the reactions that are present in the building. So under gravity loads, all the reactions are positive upwards. You have a little bit of a horizontal load on the basement wall, perhaps. But over here, you have the reactions of the building are basically countering the lateral loads. So we have a reaction over here that is going upwards, and a reaction down here that is pulling down in order to counter the overturning tendency of that lateral load. Okay, let's shift our attention to earthquakes now, seismic forces. Seismic forces are a bit different than other forces, the way that the load is imposed. They're an inertial force as opposed to an externally acting force. They have their genesis in the idea that the ground moves under the building and then the building reacts to that motion. So this is a record of the El Centro earthquake. It was a landmark event in structural engineering, and we use this as one of a suite of several earthquakes for research purposes. So it shows a number of different things moving from the bottom to the top. It shows the displacement of the ground as a function of time. It shows velocity and acceleration. So the velocity is the derivative of displacement, and the acceleration is the derivative of velocity, which makes it the second derivative of displacement. And it's really the ground acceleration that imparts the forces on the building that we have to design for. From Newton's law, we know that a force is equal to mass times an acceleration. So the way that seismic forces manifest themselves in a structure is by the acceleration of the ground times the mass of the structure. And that creates forces in the building that we have to design for, and we call them earthquake forces or seismic forces. Most of the ground motion is horizontal, so we end up with a horizontal earthquake effect. We refer to that as E sub h. But there is a small component, usually a small component, of the ground acceleration that is vertical, so we also have to design for a vertical component of earthquakes as well. Okay, the response of a building to an earthquake is a function of both the structure's mass and the structure's stiffness. So if you take 3 different structures like this, the one on the left is rather short, and it would be considered to be more rigid. It's not as flexible as the one on the right. So it has a different stiffness, so it has a different response to the structure. The one on the right, however, is one that is relatively flexible relative to its mass. So when an earthquake hits that one, that building responds much differently than the shorter buildings do. So the 2 primary parameters of a building with respect to seismic performance are the structure's mass and the structure's stiffness. Okay, Earthquake forces are considered to be lateral loads and are considered by most people to be environmental loads, but they are treated a little bit differently in most standards and specifications. Okay, fluid effects occur in tanks or other cases due to stored liquids. Stored liquids have characteristics of both a dead load and a live load, so they kind of bridge the gap between permanent and transient. One of the common cases as a civil engineer that we would run up against too are structures that retain water, like dams and weirs and things like that. You certainly could be called as a structural engineer, though, to consider things like storage tanks and water tanks for water distribution networks and things of that nature. I have a good friend in Italy who does a lot of work on seismic performance of storage tanks. Okay, the forces due to most fluids is hydrostatic, meaning that the force increases linearly with the depth of the water. So you can see here that the horizontal component of the force is a function of h. So it creates a triangular loading where the resultant P is at the 1/3 of the depth of the water from the base of the water, from the bottom of the tank. Okay, horizontal earth pressures are another force that we have to deal with in structures, and if you look at the pressures due to Earth, it's roughly hydrostatic as well. So it's equal to some constant times the self-weight of the material, or the density of the material, gamma, times the height of the fill, h. Okay, lateral pressure varies if the structure moves. If the wall or the retaining structure moves away from the soil, then the pressure is said to be active and is a smaller pressure. If a wall moves towards the soil, then the pressure is referred to as passive, and it's a much larger pressure. If the wall doesn't move, if everything is static, then the pressure is referred to as an at-rest pressure. Okay, pressure is exerted due to the backfill on the wall. So this shows a retaining structure here with a higher level of fill on the right side than on the left. And in this case, you would presume that the wall is going to be moving a little bit from right to left under the pressures that are shown there. So as such, the pressure on the right side of the wall is an active pressure because the wall is moving away from that soil. And the pressure on the right would be a passive pressure, as the wall would be moving towards that soil. So the active pressure tends to be a lot smaller than the passive pressure. Okay, and again, an at-rest earth pressure is a pressure exerted by the soil on an unyielding or an unmoving wall. Okay, let's go back to this image with the multiple-story building again. And if we look a little bit more closely at the foundations, then under the gravity loads, the foundation walls would be designed for active earth pressures, where the wall is, if it's moving at all, is moving away from the soils. But over here on the right, where we have the lateral loads acting, probably due to wind, maybe seismic, then as the building is being pushed from left to right, it's pushing against the soil on the right basement wall. And in this region here, those pressures would be said to be passive pressures, and we would have to design the wall for those. Okay, another action that we have to design for or consider in our design is that of foundation settlements. So the image on the left here, taken from the Talley textbook, shows a differential settlement in foundations on a simple portal frame. Shows it moving both vertically and horizontally. The image on the right shows a settlement in a foundation on a multiple story frame. So if we consider settlements, if the entire structure settles uniformly, then it's usually not as critical as the case where we would have a differential settlement. So here on the left, you can see we have a differential settlement here where we have some foundation displacement on the right-hand side that is different than the right-hand side. That tends to impose more forces in the building than a uniform settlement where the entire building would be translating downwards together. And then the same thing is true over here on the right-hand side. You can see that the differential settlement is creating a flexure in these beams that are adjacent to the column that's supported by the foundation that's settled. So differential settlements tend to be more critical than uniform settlements, but then again, if the entire building tends to rotate, you end up with something like the Leaning Tower of Pisa, and that creates problems as well. Okay, we'll shift our attention now to other types of loads. These loads aren't any less important than the first ones that we covered. They're just the load types that we aren't going to cover with the same amount of depth in this class. So the first one we'll talk about just briefly are construction loads. And these are basically loads that are imposed on the structure while the structure is being constructed, but they aren't loads that would be expected on the building or on the structure during the service life of the structure. And I'll use as an example the I-35 bridge in Minneapolis. Now, you guys all probably know that this structure collapsed while it was under construction, under renovation. And one of the principal reasons why it collapsed was the fact that it had a bunch of construction materials stored on the bridge itself during the if we look here, one of the reports says that we had 383,000 pounds of aggregate stored on the structure itself, and about 196,000 pounds of construction equipment that are stored on that structure. So the point that I'm trying to make here is that loads that are on this bridge during construction probably far exceeded any load that the bridge was designed for or any load that the bridge experienced while it was open to normal traffic. So this is one thing to guard against, is storage of materials on structures during construction. Here's another example. This is a situation where a precast concrete bridge was being constructed, and in order to get access for the crane, they erected a temporary bridge made out of steel using timbers as the temporary bridge deck. However, when they put the crane on the temporary bridge and tried to hoist the concrete girders, the temporary bridge collapsed and ended up putting the crane in the drink. Now, I don't know if anybody was injured in this, so I won't make light of the situation, but this is an example of construction loads, excuse me, in this case acting on a temporary structure. Another case would be in the erection of steel buildings. Nowadays, it seems like most contractors use tower cranes, but in times past, or in at least some cases nowadays, they use derricks that are actually supported by the structure itself. So you might see loads in a structure due to derricks like this during construction that might be higher than any load that the structure would see during the service life. So I'll just make one final note on construction loads. It seems like most or many accidents tend to occur during the construction of a structure, more so than during the operational service life. So it's often a part of the structure design that's not addressed directly by the engineer of record. So it's something that really should be considered, though. There are a lot of engineers out there that make their livings just figuring out how to put together or how to construct buildings and structures that are designed by somebody else. I have some good friends that focus in that aspect of structural engineering almost exclusively. Okay, crane loads are covered in both the Fenella text and the Tally text. It's not something that I'm going to discuss as a focus on in my class, but it's something that needs to be considered in a lot of buildings. Even the educational buildings like Rhodes Hall has a crane in it. A lot of buildings might even just have a jib crane or something like that in the loading dock area to help unload trucks. Okay, so cranes, have live loads, but they also create dynamic effects due to the fact that the loads on the crane actually move. There's another type of loading that warrants consideration are locked-in forces due to pre-tension and post-tensioning. These are typically for concrete, but they can be used in other types of structures as well. So with pre-tensioning, the process is that you would put cables or tendons under a high tensile stress running through a series of formworks, and then pour the concrete, let the concrete cure to some level, and then release the anchorages holding the tension in the cables. And at that point, then that tension in the cables is imparted as a compression within the concrete, and that's called pre-stressing. An alternative to pre-stressing is to cast ducts in the concrete, and then after the concrete is cured, pass a tendon through those ducts and then impose the force afterwards. And that's called post-tensioning, because in that case, the tension is imposed after the concrete is cured as opposed to before the concrete has cured. We have to account for these forces as well, though I don't know a whole lot about Post-tensioning or pre-tensioning, I focus mostly on steel structures, but it is important to consider that. Creep is another factor that comes into play, as well as shrinkage. And these are typically in concrete structures, but they can occur in other structures as well. Creep is basically a time-dependent change in concrete, and shrinkage is also a time-dependent change. The difference is that creep usually occurs under a load, and shrinkage occurs even in the absence of load. So when concrete cures, it's a hydration process. The moisture content of the concrete changes, and it causes the length or the volume to decrease in the concrete. If you don't account for these or accommodate them in some way, creep and shrinkage forces can be appreciable. I know that to be the case, particularly for bridges. Then we have temperature effects as well. And just like creep and shrinkage, if we don't accommodate temperature changes in structures by allowing it to occur without creating confinement, then temperature forces can far outweigh any other type of force that could be in the structure. So typically, in structures that are expected to experience large temperature changes, we put in expansion joints so that the structure can grow or shrink with the temperature change without imparting any forces. That would be due to a uniform temperature change, but we also have to accommodate temperature gradients as well. A temperature gradient is a temperature differential within a structure. So consider a bridge deck, just a typical overpass type structure where you have girders supporting a bridge deck. As the sun rises in the morning, it shines on the top of the bridge. The top of the bridge could get much warmer than the bottom of the bridge, maybe as much as 30 or 40 degrees. That would tend to cause the top part of the bridge to expand at a greater rate than the bottom part of the bridge. So you end up with a negative moment imparted there. The top, it would haunch upwards. And temperature gradients are important in the structures. I'll throw this slide in. Blast loading is something that is considered more nowadays than it was in the past. I don't know how many privately owned buildings are designed for blast. I don't know how many Walmarts, for instance, or even 4, 6, 8-story office buildings are designed for blast loadings. But I know that structural engineers that work on buildings for the government, particularly for military installations, have to consider blast loading as part of their design criteria. Okay, finally, I promised to define what a notional load is. Notional loads are loads that are used to represent force effects that are important in the structure but aren't modeled explicitly. Notional loads are not developed to resemble an actual load in the structure. So as an example, we have to consider differential settlements in the design of our buildings, but modeling a settlement of a foundation is challenging in a lot of different aspects. There are a lot of different combinations of differential settlement that could be considered. So as an alternative to explicitly modeling this differential settlement of a foundation, many engineers will put a lateral load on the building that is small compared to wind or seismic, but that lateral load gives moments or shears or axial forces in the building that are representative of what might be expected if a actual differential settlement occurred. Another case would be when a building is constructed or designed, you have to consider the fact that the building might not actually be erected in a perfectly plumb situation. It might not be perfectly vertical. It might have some initial out of plumbness. In order to consider that explicitly, that would be very challenging. You would have to develop a computer model where the building is a little bit out of plumb. So rather than considering that explicitly, a lot of engineers will put a notional load into their model that gives, it's usually a lateral load, that gives bending moments, shear forces, or axial forces that one might expect due to the initial imperfections or initial out of plumbness of the building. Usually, these notional loads are prescribed as a percentage of the gravity loads. So if you have a dead load and a live load given, you might say that the notional load is a percentage, 1% of those gravity loads, for example. All right, that brings us to the end of this lecture. Hopefully by now you have a good understanding of the different types of loads that act, how they're categorized, and what different types of actions they impose on a structure. In the next lecture, we'll talk about different philosophies that are used in design, and then after that, we'll come back to the third lecture in this module where we talk about combinations of loads that act on structures. Thanks.